I want you to imagine, just for a second, that you are walking a tightrope.
Oh boy.
Yeah, and it is suspended incredibly high up. And leaning even like a fraction of an inch to the left or a fraction of an inch to the right spells total disaster.
Yeah.
Take that image and apply it directly to your own bloodstream. That tightrope is your blood's pH, which is strictly held between 7.35 and 7.45. I mean, it is an incredibly narrow window for survival.
It really is. It's essentially a chemical mandate.
Yeah.
Because if your blood strays outside that tiny 7.35 to 7.45 window, the proteins and the enzymes that run every cellular process in your body, they begin to denature.
Like they just fall apart.
Yeah, they literally unfold and just stop working.
Yeah.
So when we talk about the body seeking balance, we aren't talking about some casual preference. We are talking about a moment-to-moment fight for structural integrity.
And that sets the stakes perfectly for the mission of today's deep dive. We are unpacking the unsung heroes of this incredible balancing act, which are your kidneys. We're pulling from a really comprehensive anatomy and physiology overview on renal acid-base regulation. And the goal here is to move way past that high school biology idea of kidneys as just, simple passive filters.
Like the old waste treatment plant idea.
Exactly. We're going to look at them as dynamic, highly adaptable chemical laboratories that are constantly guarding your body's pH.
Because usually, when people think about regulating acidity or pH, they immediately think about breathing.
Right. And I like to think of the lungs and the kidneys as this dynamic duo of disaster response. Like the lungs are the first responders. They show up with the sirens blaring, putting out the immediate fires by blowing off carbon dioxide.
Yeah.
But the kidneys are the long-term structural engineers. They show up a few days later, clearing the rubble, pouring new concrete, and basically rebuilding the city's infrastructure to make sure the environment is actually stable.
That's a great way to look at it. And to give you a sense of the sheer scale of the engineering project the kidneys are running, we just had to look at the daily numbers. Every single day, your kidneys filter 180 liters of plasma.
Which is just wild to think about.
It is. And while they're doing that, they are dealing with roughly 4,300 milliequivalents of bicarbonate.
Which is the body's primary acid buffer, right?
Exactly. And on top of managing all that recycled buffer, they have to synthesize a way to neutralize 50 to 100 milliequivalents of what we call fixed acid.
Fixed acid.
Yeah, which is generated purely from your daily diet and your cellular metabolism.
That is just a staggering workload. But before we get into the actual cellular machinery of how they pull that off, I'm curious how scientists even map this out in the first place, because understanding an invisible chemical balance inside a living organ doesn't just happen overnight.
Oh, no, not at all. It took about a century of chemistry and physiology basically building on itself piece by piece. The theoretical foundation was laid in the early 1900s by Lawrence Henderson and Carl Albert Hasselbalch.
Ah, yes.
Yeah, they provided the mathematical backbone for this entire field with the Henderson-Hasselbalch equation.
Right, which is the bane of many chemistry students' existence. But I assume it was a massive breakthrough at the time.
It fundamentally changed medicine. Before that equation, physicians could really only talk about acid-base balance qualitatively.
Yeah.
Like, they knew blood got acidic, but they couldn't map the actual mechanics.
Oh, interesting.
Yeah, Henderson and Hasselbalch gave us the math to quantify exactly how bicarbonate and carbon dioxide interact to set blood pH. And that equation allowed physiologists to finally ask, how much of this regulation is the kidney's job and how much is the lungs.
But, math on a chalkboard is just theory until you can physically measure it in a patient.
Right, which brings us to Donald van Slyke in the 1910s and 20s.
Yeah.
He invented the actual manometric tools to physically measure CO2 and bicarbonate in blood. So he turned that theoretical math into a clinically measurable reality.
Wow.
But to actually understand the kidney's role specifically, we have to jump to the mid-20th century with Robert Pitts.
Okay. He conducted these foundational whole kidney experiments using dogs, employing clearance techniques to see exactly how the organ responded to different acid loads.
And what fascinates me about Pitts is that he was actively pushing back against the scientific establishment of his era.
He really was.
Because the prevailing model back then was championed by this very prominent physiologist named Homer Smith. And Smith's entire focus was on how the kidney filtered water-soluble waste, like urea. He basically viewed the kidney as a sophisticated waste treatment plant and largely missed the whole pH story.
Completely missed it, yeah.
So Pitts had to come in and prove that the kidney is actively defending the blood's acidity, which I think brings up this critical division of labor we need to talk about, the volatile acid versus fixed acid.
That distinction is everything. Your cellular metabolism produces a massive amount of volatile acid. We're talking about 15,000 to 20,000 millimoles of CO2 every single day.
And we call it volatile because it can easily be converted into a gas and exhaled by the lungs in a matter of minutes. But your metabolism also produces those 50 to 100 milliequivalents of fixed or non-volatile acid. And this is a byproduct of breaking down dietary proteins and the incomplete oxidation of fats.
Okay, I want to push back on this division of labor for a second, because if I'm looking at the timeline, the lungs are incredibly fast. They can alter our pH in minutes just by changing our respiratory rate.
Right.
So why do we even need the kidneys to handle acid? Why can't we just, hyperventilate our way out of a high-protein, high-acid diet?
Well, it comes down to the physical state of the molecules.
Yeah.
We literally cannot breathe out of steak.
Right, that paints a picture.
Right. The acids generated by protein breakdown, things like sulfuric acid and phosphoric acid, they just cannot exist as a gas at human body temperature. They are physically fixed in the fluid of your bloodstream.
Oh, I see.
So your lungs can blow off extra CO2 to temporarily shift the mathematical ratio and buy you some time, but those fixed acid molecules are still circulating, threatening to drop your pH.
They're trapped.
Exactly.
Yeah.
The only physical way out of the body for fixed acid is down the drain through the urine, and ramping up that excretion takes the kidneys days, not minutes.
Okay, the limitation of the lungs makes perfect sense now. So since the kidneys have to handle this fixed acid, they need a buffer to neutralize it so it doesn't just eat away at our internal tissue on the way out.
Yes.
And that primary buffer is bicarbonate. So the kidney has two highly distinct jobs here: saving the massive amount of buffer we already have and generating brand new buffer to replace what gets used up. Let's start with saving the buffer, the Great Recycling Act.
Yeah, consider that 4,300 milliequivalents of bicarbonate being filtered through the kidneys every day. If you didn't have a mechanism to pull that back into the blood, you would pee out your entire buffer reserve in a matter of hours.
Which would be catastrophic.
The result would be fatal systemic acidosis. So the first section of the kidney's plumbing, the proximal tubule, reabsorbs 80 to 90% of it. But it does this through a highly convoluted chemical relay, because bicarbonate cannot easily slip across the tubule cell membrane.
And this is where we need to dispel a very common misconception. People tend to think of the kidneys as this passive sieve, like a colander draining pasta where the bad acid falls through and the good buffer is simply held back.
Right, but it's not.
Exactly. This is a highly active, energy-intensive process of secretion. Walk us through how this chemical relay actually works.
So it requires a highly coordinated sequence of enzymes and transporters. First, a transporter on the cell surface called NHE3 actively secretes a hydrogen ion. That's an acid molecule. It secretes it out of the cell and into the tubule lumen where the urine is forming.
Okay.
That secreted hydrogen ion binds to the filtered bicarbonate floating in the fluid, forming carbonic acid. Then, an enzyme sitting right there on the lumen surface called carbonic anhydrase phase immediately breaks that carbonic acid down into CO2 and water.
Oh, because CO2, being a gas, actually can cross the lipid cell membrane.
Precisely. The CO2 easily diffuses back inside the proximal tubule cell, and once inside, the cell deploys a different version of that same enzyme.
Oh, really?
Yeah, carbonic anhydrase II, which runs the exact same chemical reaction but in reverse. It takes the CO2 and water and converts it back into bicarbonate and a hydrogen ion. The hydrogen gets sent back out to grab another molecule, keeping the cycle going.
And the bicarbonate, how does it actually get back into the blood?
That is the final crucial step. A transporter on the blood side of the cell called MBCE1 acts as the exit door. It shuttles that newly reassembled bicarbonate out of the cell and safely back into the systemic circulation.
So to make sure I have this right, is it kind of like sneaking a massive piece of flat pack furniture into an apartment? Like the fully assembled bicarbonate is too big and structurally awkward to fit through the front door of the cell?
That's a good way to look at it.
All right, so you break it down on the sidewalk into CO2 and water, you carry those flat pieces inside, you reassemble it in the living room, and then you just push it out the back door into the bloodstream.
That captures the mechanics perfectly.
Yeah.
The lipid membrane is the narrow door, and the carbonic anhydrase enzymes are the tools you use to assemble and disassemble the molecule.
But reclaiming bicarbonate isn't enough to solve the daily fixed acid problem. Reclaiming is just, preventing money from falling out of a hole in your pocket.
Exactly.
You aren't getting any richer, you're just not losing the cash you already have. But neutralizing that daily 50 to 100 milliequivalents of fixed acid actively consumes bicarbonate. You're spending the money.
Right, it's gone.
So to survive, the kidney has to generate an entirely new paycheck. It has to make new bicarbonate. How does it do that?
It relies on, well, two primary mechanisms. The first is titratable acid, which basically involves pumping hydrogen ions into the urine and trapping them there with phosphate buffers. And for every acid molecule permanently trapped and excreted this way, a brand new bicarbonate molecule is generated inside the cell and sent to the blood.
Okay.
But the second mechanism is far more powerful and adaptable, and that's ammoniogenesis.
Oh, ammoniogenesis. I know the scientific consensus on this has shifted significantly over the years. What did we get wrong initially?
So the old textbook model, dating back to Robert Pitts, treated ammonia production like this static background hum. It was viewed as a fixed capacity process. But starting in the 1970s, researchers like Norman Kerthoys revealed a complete paradigm shift.
What did you find?
That ammoniogenesis in the proximal tubule isn't static at all. It is driven by the active metabolism of an amino acid called glutamine. When the body is hit with a sustained acid load, the kidney doesn't just work harder. It actually actively reprograms its own gene expression to ramp up the enzymes required for glutamine metabolism. Yeah, it can increase its ammonia excretion several-fold within just a few days. It is the kidney's most dynamic, heavy-lifting response to an acid crisis.
The idea that the kidney dynamically reprograms its own metabolic pathways on the fly just to manufacture more buffer is incredible.
It's amazing.
So the proximal tubule handles this massive bulk workload, right? Recycling 90% of the buffer and ramping up ammoniogenesis. But if we go back to that tightrope, balancing the blood perfectly at 7.4, bulk work isn't enough. You need precision.
You do. And that precision happens further down the line in the distal nephron, specifically in the collecting duct. This is where we meet basically the smart cells of the kidney, the intercalated cells.
By smart cells.
Yeah, they function like a highly sensitive bidirectional thermostat for your body's pH. And they come in two distinct opposing types, type A and type B.
Let's look at the mechanics of these smart cells. What does type A do?
Type A, or alpha cells, are your ultimate defense against acidosis. They actively pump hydrogen ions into the urine and save bicarbonate. And their sheer power is staggering. If you look at the concentration gradient, your blood pH sits around 7.4. But during a severe acid load, these type A cells can drive the urine pH all the way down to 4.4.
Wait, because pH is on a logarithmic scale, right? So a
Right.
drop of 3 points means the urine is 1,000 times more acidic than the blood?
Exactly. 1,000 times. The type A cells are pumping hydrogen ions against a 1,000-fold concentration gradient. I mean, it requires an immense amount of cellular energy to force acid into an environment that is already deeply acidic.
That's intense.
It is. And then you have the type B, or beta, cells. They do the exact mirror opposite. When the blood is too alkaline, type B cells use a specific transporter called pendrin to secrete bicarbonate into the urine while reabsorbing acid back into the blood.
Okay, I have to pause on the type B cells because it makes total evolutionary sense that we developed an emergency system to dump acid against a massive gradient since our metabolism constantly generates acid.
Right.
But why would the human body ever evolve a dedicated system to actively throw away our precious bicarbonate buffer? I mean, under what scenario do we ever have too much base?
Well, to understand why the type B cell is so essential, we have to look at what happens when environmental extremes, or even medical interventions, push this thermostat to its limits. The classic real-world stress test is high altitude.
Oh, sure. So if you travel to a massive elevation, the air is thin, oxygen drops, and your immediate reflex is to start hyperventilating.
Right. And because you are hyperventilating to get oxygen, you are simultaneously blowing off massive amounts of CO2, your volatile acid.
Ah, I know where this is going.
Yeah, this rapidly drives your blood pH up, creating a state of respiratory alkalosis. And this is the exact scenario the type B cells are built for.
Okay.
Over the next 2 to 4 days, the kidneys register that the blood has become dangerously alkaline. So the type B cells activate and intentionally dump bicarbonate into the urine to bring your systemic pH back down to that 7.4 tightrope.
Which perfectly explains the timeline of altitude acclimatization. You don't acclimate the moment you step off the plane. You have to wait days for the kidneys to physically reconstruct your blood chemistry.
Yes. And understanding that timeline brings up a really fascinating medical intervention, because mountain climbers often take a drug called acetazolamide, widely known as Diamox, to prevent altitude sickness.
I've heard of that.
Yeah, and Dimox works by directly inhibiting carbonic anhydrase, which is the enzyme discovered by scientists Meldrum and Wrighton back in the 1930s.
Wait, carbonic anhydrase? That's the exact enzyme from the flat pack furniture relay race we discussed earlier, the one that reclaims our filtered bicarbonate.
Exactly. So by taking Dimox and blocking Meldrum and Wrighton's enzyme, the kidney temporarily loses its ability to reabsorb bicarbonate. You end up peeing it out, which causes a mild, self-inflicted metabolic acidosis.
Oh, wow.
Right. By making your blood artificially acidic, you trick the respiratory center in your brain into breathing faster and deeper even before you reach extreme altitude. You're essentially jump-starting the acclimatization process.
It's like deliberately tricking your home's thermostat into thinking it's freezing inside, just to force the furnace to kick into overdrive before the actual winter storm hits.
That's brilliant.
It is a very clever hack of the physiology. But we also see scenarios where the system is subjected to a nightmare stress test. Take salicylate toxicity, basically aspirin poisoning.
Okay, what happens there?
Aspirin attacks the acid-base system from both ends simultaneously. The salicylate directly stimulates the brain's respiratory center, forcing intense hyperventilation and causing respiratory alkalosis.
Oh, no.
But concurrently, it uncouples cellular energy production, which floods the bloodstream with organic acids and triggers a profound metabolic acidosis.
So the lungs are trying to pull the pH up, while the cellular metabolism is violently dragging it down. I mean, the entire system is in chaos.
Precisely. It creates this deeply conflicting clinical picture that doctors rely on to diagnose the toxicity. But, beyond these acute crises, the source material highlights a really interesting debate about chronic everyday stress on this system, particularly regarding the modern diet. The net acid load of diet debate. I know researchers like Anthony Sebastian and Linda Frassetto have analyzed the ancestral hunter-gatherer diet and compared it to what most of us eat today.
They have. And the core argument is that modern diets, which lean pretty heavily on animal proteins and cereal grains, and much less on alkaline fruits and vegetables, well, they impose a chronic, low-grade metabolic acid load on the body day in and day out.
And that's driven by those sulfuric and phosphoric acids from protein metabolism we mentioned earlier.
Right. And the theory posits that to buffer this continuous decades-long acid load, the kidney's ammoniagenesis might not be entirely sufficient. So the body may begin tapping into its largest emergency reserve of base,
Which is?
the skeleton. Human bones contain massive amounts of calcium carbonate. And the debate centers on whether this modern dietary acid load slowly forces the bones to release calcium carbonate into the blood to buffer the acid, potentially driving long-term bone demineralization and muscle wasting as we age.
Now, I want to be absolutely clear for anyone listening. This is a live, highly contested debate in nutrition and physiology.
Yeah.
It is definitely not settled science.
No, absolutely not.
Because critics strongly point out that healthy kidneys maintain perfectly normal serum bicarbonate levels in people eating high-protein omnivorous diets. And they argue that the renal system handles the load exactly as it evolved to do without actively destroying bone.
Right.
So we are certainly not taking a side here, but it brilliantly highlights how interconnected renal chemistry is with the rest of the body.
It definitely shows that you can't view the kidney in isolation. But, everything we've discussed so far assumes the machinery is actually working.
Yeah.
What happens when the cellular architecture we've been mapping out fundamentally breaks down?
Well, in medicine, you often understand a complex system best by analyzing its failure modes. And in the kidney, these failures are categorized as renal tubular acidosis, or RTA, and they map flawlessly onto the anatomy we've discussed.
They really do. Let's look at type 1, or distal RTA. This is a specific failure of those type A intercalated cells in the distal nephron. They lose the mechanical ability to secrete hydrogen ions into the urine.
Which means the acid just backs up into the systemic circulation.
It does. And what is so striking here is the failure of the gradient. Normally, as we noted, the kidney can drive urine pH down to 4.4.
Right, that 1,000-fold gradient.
Exactly. But in type 1 RTA, the cells fail to pump against the gradient, and the urine pH remains stuck above 5.3, even while the patient's bloodstream is becoming dangerously acidic.
This completely shatters that popular wellness trend that claims you can just pee on a pH strip and determine your internal systemic health.
Oh, completely.
Because if you suffer from type 1 RTA, your blood is drowning in acid, but your urine looks perfectly fine or falsely alkaline on a strip.
A urine pH in isolation can be incredibly misleading. And then we have type 2, or proximal RTA, and this is a failure of the bulk recycling center. The proximal tubule simply fails to reabsorb the filtered bicarbonate, allowing it to spill out into the urine, which rapidly depletes the body's primary buffer.
And there is also type 4 RTA, which I find fascinating because it breaks one of the most common medical rules of thumb regarding electrolytes.
It does. A lot of medical students learn the shortcut that, systemic acidosis usually presents with low potassium. But type 4 RTA is driven by a deficiency in aldosterone.
And that's a hormone.
Yeah, a hormone that normally stimulates the secretion of both acid and potassium into the urine. So when aldosterone is missing, you get a unique dual failure. The patient develops systemic acidosis coupled with dangerously high potassium levels.
Wow. I want to touch on one more breakdown because the logic behind it feels so counterintuitive. Diuretic-induced alkalosis. When patients take loop or thiazide diuretics, they lose a significant amount of fluid volume, and the kidney reacts to this in a way that seems almost reckless.
It basically panics. When systemic blood volume drops significantly, the kidney's overarching priority shifts from maintaining perfect pH to sheer volume conservation.
It just wants to hold on to whatever it can.
Exactly. It needs to hold on to sodium and water at all costs to maintain blood pressure. To accomplish this, the tubule machinery paradoxically reabsorbs extra sodium alongside extra bicarbonate, and that drives the blood pH up into alkalosis, even though that is chemically the wrong move for acid-base balance.
So, if we look at the hierarchy of survival needs, the kidney will actually sacrifice our blood's perfect 7.4 pH if it means holding on to enough water and salt to maintain blood pressure.
Absolutely. It comes down to immediate lethality. If your blood pressure drops to 0, you die in minutes. If your blood pH shifts to 7.5, your enzymes might be stressed, but you have time to correct it. The kidney always chooses the lesser evil.
That makes total sense. If we synthesize this entire journey, it really reshapes how you view this organ. I mean, we've gone from the massive bulk recycling operation of the proximal tubule, saving 90% of our buffer using that ingenious CO2 diffusion trick across the cell membrane,
Yep.
to the dynamically reprogrammable glutamine-fueled factory of ammoniogenesis, making new buffer on demand. And finally, to the precise 1,000-fold gradient fine-tuning of the intercalated cells in the distal nephron. The kidney is infinitely more sophisticated than a passive sieve.
It is a highly responsive, adaptable chemical plant. And the mechanics we've walked through matter right now in intensive care units everywhere.
Right.
When an ICU doctor runs an arterial blood gas, looking at a patient's exact pH, CO2, and bicarbonate, they are literally reading the real-time dialogue between the lungs and the kidneys.
Yeah.
When a patient with diabetes goes into diabetic ketoacidosis, or DKA, the profound illness occurs because their pathological metabolic acid production has completely overwhelmed the kidney's maximum capacity for ammoniogenesis.
The system just hits its absolute physical limit.
It does.
Which brings me to a final provocative thought to leave you with, one that builds directly on the physiology we've explored today. We know clinically that as patients develop advanced chronic kidney disease, or CKD, their overall filtration rate drops, and their tubules lose the cellular ability to perform adequate ammoniogenesis.
Right. They can't keep up.
Exactly. They physically cannot generate enough new bicarbonate to neutralize the daily acid of just being alive, which is why they are frequently prescribed oral baking soda, sodium bicarbonate, as a daily medication.
Yeah.
But consider this. Kidney filtration rate naturally declines in all of us as we age. It is a standard part of getting older. If that is true, could the mild natural aging of our kidneys be quietly shifting the burden of buffering our daily metabolic acid?
Oh, wow.
I mean, if our 70-year-old kidneys can't manufacture quite as much ammonia as they did at 20, our bones slowly, imperceptibly dissolving over the decades, surrendering their calcium carbonate just to keep our blood balanced on that perfect 7.4 tightrope.
It is a profound physiological question. It forces us to acknowledge that every tightly regulated balance in the body likely has a hidden cumulative cost somewhere else in the system.
It really does. The next time you take a drink of water, maybe give a little nod of respect to the incredible chemical engineers working silently in your lower back. Thank you so much for joining us on this deep dive. Keep questioning the science, keep wondering about the mechanisms, and keep marveling at the amazing machinery hiding inside your own body. We'll see you next time.